Okay, so here's what we were talking about last time, gravity. So again, quick reminder, here's the old formula that everybody saw in high school. You had like a physical science class in high school. We talked last time about how that can be rewritten, sort of more appropriate for a multivariable calculus context, as a vector field. So let's think of this as something that's not a force that's between two masses, but let's think of this as something that's created by a single mass. Right? And if you want to know what the corresponding force is, then, okay, this is acceleration. You have to multiply by the other mass to get the actual force. So this, you might, instead of calling this a gravitational force field, you might call it a gravitational acceleration field. Okay. And we talked last time about how there is a cube in the denominator. Seems surprising, but that's actually consistent with the inverse square formula above. Okay. All right. So the very last observation we made was that, amazingly, this formula has the feature that its divergence is 0. It's a really surprising fact. You wouldn't think something this complicated, right, would have the feature that when you do this calculation, that just all the terms just cancel. And amazingly, you get 0 everywhere, with one notable exception, of course, and that is at the origin. If you think about it, at the origin, this vector field is not even defined. Right? So the vector field only makes sense away from the origin. All right. So this is not only surprising, it's also really important. This is going to be a fact that we're going to use to great effect in the following several examples. Where we're going to get some really powerful conclusions about gravitational fields. Okay, so the first one's an easy calculation. We're going to start with, suppose we have some object of mass m sitting outside of a region, solid three-dimensional region R, right? And I want to compute the flux. What is the flux of the gravitational field through that region? So here's our picture. Here's our region. Right? Solid three-dimensional region. And here's the corresponding mass. Right, you've got a mass there. And that mass creates a gravitational field. Now, gravitational fields point toward the mass. Right? And the further you get away, the shorter they are. Right? So there's that inverse square proportionality. Now, if we were to look at this picture and ask the question, how much flux is there through this surface? You would say, wow, this is a really hard problem, because look at this vector field. This vector field is not constant. This vector field is, it's a formula. It's the formula we have on the previous page, which has a radius to the third power in the denominator in the formula, which means we have x squared plus y squared plus z squared to the 3/2. So this has square roots in it. This formula for this vector field has square roots in it. Square roots that are cubed, no less. It's an ugly vector field. And we have some surface that's, lumpy and bumpy. It's not like it's a nice, straight-edged or, perfectly spherical or something convenient like that. This is an arbitrary, random, lumpy shape. This looks like a really hard problem to compute that flux, right? You imagine yourself parametrizing this surface, and after parametrizing those weird formulas for position on the parameterization, then go into this really ugly formula for the vector field, and then you have to do the surface integral. It seems like a nightmare. It's actually really easy calculation. We're interested in computing boundary flux. Gauss's divergence theorem tells us that boundary flux is a triple integral of divergence. The divergence we just got through agreeing is 0. So this integral is 0. Everybody see how that works? This is a lot easier than we thought it was going to be, if you think about it. Okay, so it's a really powerful fact. And this observation about how the divergence of the gravitational field is 0 is pretty awesome. All right. Now, before we go on to the next calculation, I just want a quick context thing. There are several different ideas that get tossed around here, kind of together with each other. You just have to make sure to distinguish between these things. On the one hand, there's the gravitational field, Right? That's the thing that you can kind of sort of, I'm going to say visualize, right? That's the thing you most easily relate to. Then there's flux of the gravitational field. Separate thing, right? Then there's the divergence of the gravitational field. So all these things are related to each other in different ways. Flux is related to the gravitational field by a surface integral. Divergence is related to the gravitational field by way of, well, it's a computation, it's a formula. It's compute the divergence, right? And flux and divergence are related to each other by way of a triple integral, Gauss Divergence theorem. So there's really a lot going on in this calculation, even though it's like one line. Okay. All right, now an important fact that went into this calculation, let's go back to the picture. I needed to be able to relate this surface with what I'm going to call its interior, or said differently, I needed to relate this solid to its boundary surface. And I made an argument about Gauss's divergence theorem as it applies to this solid and its boundary surface. Well, here's the thing. A very important fact that I took advantage of here is that the gravitational field is perfectly well defined, no problems, everywhere on this solid and its surface. Right? And the reason is because the problem is way over here. That's where the mass is. This, where the mass is that's where the vector field is undefined. Right? We talked about that a minute ago. If x is equal to 0, if you're at the point where the mass is of the gravitation that's creating the gravitational field, the vector field isn't defined at all, and that's bad. Okay? So just like the fundamental theorem of calculus, y'all probably remember examples from Calc 1, Calc 2, depending on when it gets done, where if you have if the function fails to be defined at a single point in the interval, fundamental theorem of calculus does not apply. It's not even close, right? It's not it was just 1 point, so does it really matter? Yeah, it matters a lot. Okay, so ditto for Gauss's divergence theorem. We need the vector field to be defined everywhere, and as far as we're concerned, on this question, it is. Okay, so now let's consider a related question, which is, suppose what happens, let's try to figure out what happens if the object M is inside the region. So this is not a crazy scenario, right? It's just this scenario here where here's let me draw our solid here. Got that solid, and it's got a boundary surface. And it's not the craziest thing in the world to speculate that there might be a piece of mass sitting there, and I might want to compute the flux through this boundary surface of the gravitational field created by that mass. It's a fair question. Right? The vector field that I'm interested in is perfectly well defined everywhere on the surface where I'm computing the flux. So flux is a well-defined thing, and so that's a reasonable question. But of course, per my speech from 30 seconds ago, the divergence is not defined. The vector field is not defined everywhere on the interior. The divergence is not defined at this one point because that's where the mass is. Right? So we cannot just, in this case, we cannot just cite Gauss's divergence theorem. But it remains, though, that the question was still a reasonable question. The vector field itself is perfectly well defined on the surface, and I can still want to know what is the flux through that surface. So the tricky move here is to pull a fast one, and that is to say we're not going to consider the solid that is in question exactly. What we're going to do is we're going to consider this solid. It's the same solid, but where a little ball has been hollowed out around where the mass is. Right, so it's a hollow lump, kind of. Right? And, well, the vector field is perfectly well defined everywhere in that yellow solid that I'm calling R0. divergence is perfectly well defined everywhere on this yellow solid R naught. And so I can write down Gauss's divergence theorem for this yellow solid R naught. It's not going to give us exactly what we want, but what we want is going to be part of what we get. So here's what we get. Gauss's divergence theorem applied to that solid. Triple integral of divergence. And then we have flux on the boundary of the solid. Now we have to think through, what is the boundary of this yellow solid? The boundary of this yellow solid has two chunks. There's that chunk, and then separately there's this chunk. Yeah, makes sense. And if you think about orientations, of course, boundary goes like that on the outside chunk, but it goes like that on the inside chunk. And so when you write down that flux in total, what we have is the boundary flux that we're interested in, but unfortunately then minus the boundary flux on that little small sphere. So we have not gotten an answer to our question. Our question initially was, what is this thing? And this does not tell me, because even though I can do that calculation and get 0, there's the looming, yeah, but what's that other thing? Right. What I do have, though, even though it's not an answer to my question, I do have that these two things here have to be equal to each other because their difference is 0. That make sense to everybody? Okay. Now, who cares about that? So the reason this is interesting is because if you go back to this picture and let's say, okay, so here's our, we've got a mass, certain amount of mass at this location. We ask, what is the boundary flux there? And our answer was, well, I don't know, but it's the same as the flux through that little sphere. Okay, what do I do with that? Well, here's an argument I can make now. If I were to take that little piece of mass and move it over to here, right? And well, now how much boundary flux is there through the purple surface, given that the green mass is now way over here? Well, I can make the exact same argument. Okay? And so the purple flux is equal to the flux through the yellow sphere of this green mass's gravitational field, which is going to be exactly the same as that one was, which is exactly the same as that one was, which is what it doesn't really matter where this picture is. This amount of mass with a little ball around, a little sphere around it. That's pick your radius. I don't really care. That amount of flux, it's the same calculation wherever you might happen to be, just in a different place. So what do we get out of this? What's really the most valuable about this argument? It's not that we've computed what this flux is. We haven't. What we've computed, what we've shown, is that the amount of flux, this amount of flux that we're interested in, does not depend on where the mass is inside of that surface. The mass could be anywhere. Put the mass wherever you want. I don't care. It doesn't matter where you put the mass. You're always going to get the same answer because of this argument. Okay. So this is independent of where you put the mass. Therefore, that is independent of where you put the mass. Okay. All right. So that's kind of wild if you think about it. Let's just take a moment to dwell. You look at this picture and you think, well, my gosh, if I take this mass and if I move this mass over here, the gravitational field changes dramatically. When the mass is at this location, right, the gravitational field, maybe I better do this with a pencil. The mass is at that location. The gravitational field at, let's say, that point is like that. But when you move the mass up to here, at that same point, the gravitational field is now like that. It's ditto everywhere. As you move the mass, the gravitational field on the surface is changing everywhere. And yet, amazingly, the flux of that constantly changing gravitational field is constant. So it's a really surprising result and really interesting. And it's going to turn out to be really useful. Okay. All right, so now we want to consider a more general scenario. I want to think about our gravitational field here. And I'd like to compute consider a scenario where we don't just have a point mass. Okay, so if you think about it, this is an oversimplification. I mean, there's no such thing as point mass, right? Mass is typically in a thing that has some size. Like this has got a certain amount of fatness to it, right? You can't take mass and actually concentrate it at a single point. Mass is usually distributed over space. So if mass is distributed over space, either in a relatively small object like this pen, or now let's make it harder, what if we were looking at like a gaseous cloud? A lot of total mass, but distributed over a lot of area. What can I conclude about that gravitational field that's created by that? And the very first observation I want to make is this is a nasty seeming problem. I'm going to draw a picture of what we're contemplating here. So there's a bunch of mass, and just for effect, I'm going to fill it in in an unequal way. So we have less mass density over here, a little bit more mass density here, even more there. Quite a bit of concentration of mass there, but nevertheless, there is still mass kind of distributed over a whole wide area. What kind of gravitational field does that create, I ask, there? What's the gravitational field at this point? Well, nightmarish looking calculation. Because if you think about it, again, not having a point mass, that means that, well, look, this piece of mass there is going to make the gravitational field want to do like that, but this piece of mass there makes the gravitational field want to do like that, and you see the pattern. This piece of mass here makes the gravitational field want to do like that. There's bazillions of little particles, each of which are creating their own little microscopic little gravitational fields at this point. And I would have to add up the corresponding little gravitational fields created by all of the little atoms or molecules, or however you want to break it down, of gas in the entire cloud. So that looks like a horrendous calculation. Now, suppose we take it a step further. And suppose not only do I want to know what the gravitational field is, but I would like to know the divergence of that gravitational field. Please. It's a completely intractable sounding problem, so it would seem. And yet, with some clever arguments, we're going to be able to answer this question momentarily. So, here's the idea. We're going to consider a little sphere around that point. Right. Now keep in mind, I'm interested in computing the divergence of the total gravitational field at that point. The way I'm going to get at that is I'm going to start by computing the flux through this sphere. It'll all come together at the end. How am I going to compute the flux of the gravitational field through this sphere? Geez. Seems like a nasty problem. But we already know a couple of things. Here's the first thing that I know. From our first example, if I have a surface, and if I'm interested in the divergence of the gravitational field through that surface, any mass that's outside of the surface contributes nothing, right? We already considered a mass outside of a solid region, outside of the boundary of a solid region, and the flux contributed by that mass, gravitational flux created to that surface, is zero. So I get to ignore most of this mass. I just pretend that most of that mass is not there. Now I emphasize that I'm not saying that this mass does not contribute to the gravitational field. Of course it does. Yeah, it definitely affects the gravitational field. But since I'm interested in the divergence of the gravitational field, and more immediately, I'm interested in the flux through this surface of the gravitational field. Flux is completely unaffected by the mass outside of that surface. So, toss it. Now, of course, there's still a little bit of mass inside. But our problem just got a lot more tractable looking. Right? Okay, next step in the calculation. Let's see here. I've got a bunch of mass on the inside of this sphere, but again, that mass is distributed all throughout the sphere and, all over the place throughout the sphere. And how do I write down the gravitational field created by all those little particles? Oh my gosh, it seems like a hard problem. Well, here's where we use the second fact that we just talked about earlier. And that is, when you do have a mass inside of a boundary surface, it doesn't matter where the mass is. The mass could be here, it could be there, it could be over there, it could be over here, whatever, anywhere inside of the solid. It doesn't matter how the mass is distributed or where the mass is. Only how much mass matters. Right? So I am welcome, by the argument that I made previously, to take mass wherever it might be and decide, you know what, I'd like to put it right there instead. So I'm going to do that in this scenario. Where'd my picture go? Here it is. I'm going to do that in this scenario. I'm going to take all that mass. Oh, let's see here. Hang on. I need to see if I can. Yeah. I'm going to take all that mass and concentrate it all at the very center of that ball. Right? I'm totally welcome to do. All I did is rearrange where the mass is. I'm just compressing all that mass down to a single geometric point. And now we have a highly plausible problem of I've got a point mass, and I want to compute the flux of the gravitational field through the sphere. Point mass, gravitational field is easy to write down. Sphere, easy surface. This is coming together. Right? What seemed like an intractable problem has now turned itself into a perfectly doable problem, and the calculation is right here. Want to compute the flux. There's our formula for flux, which of course you can rewrite like that. Alternative formula for flux. Our gravitational field, we just agreed, is that. Okay. Let's think about our normal vector. Well, conveniently, this is a sphere. Spheres have lots of symmetries. The normal vector to a sphere, whoops. That being the center, dotted line. The normal vector points in the same direction. Oh, I did that in blue. Hang on a second. I want that in blue. The normal vector is just the unit vector pointing in the direction of the position vector x. So, little n, x divided by magnitude of x. So, we've got ourselves an integral to compute here. And this turns out really well, as it turns. If you think about it, we're looking at a little sphere of radius r. So if the sphere is radius r, all of this junk simplifies really well. That simplifies to 1 over r squared. Now let's just follow that through. We have x dot x. That gives me magnitude of x squared. We have magnitude of x to the fourth in the denominator. That leaves us with just 1 over magnitude squared, which is 1 over r squared. So most of that integrand just simplified into a constant, which is awesome. This constant, of course, just pulls right out. Right, and all we're left with is surface area. And I hope you all remember the formula for the surface area of the sphere. That's a Barnyard variety geometry formula from the high school geometry 4 pi r squared. So this is all over at this point. The r squareds cancel, and you're left with just negative 4 pi gm. It's a really cool calculation. A lot just happened here. We had this horrifying problem of massive gas cloud, mass distributed over all of different places, gravitational fields pulling you every which way. And yet we've concluded that if you pick a sphere, the flux of the gravitational field through that sphere is easy formula. Okay, now where we turn this into divergence is with this observation that this flux that I just computed, I can also compute it with the divergence theorem. Flux is triple integral of divergence. We're looking at a really small little sphere here. On small spheres, the function's approximately constant. At the integrand's approximately constant, then it's just integrand times volume. So, punchline then, we have concluded that that is equal to that, and from there I can then solve for divergence. You can see we get mass divided by volume gives me density. And so there's your formula for the divergence of gravitational field. It's a shockingly simple result. Let me just remind you what a nasty problem this was. We had a mass distributed all sorts of different places, gravitational fields pulling you every which way. Hard to imagine how we would even get to writing down the gravitational field itself. We posed the further, seemingly more difficult question of what is the divergence of that gravitational field? And it turns out that after all is said and done, it doesn't really matter about most of the mass that's involved in the cloud that's contributing to the gravitational field doesn't contribute at all to what the divergence is. Only the mass density where you are contributes to the divergence. Okay. All right, so there's some nice ways to think about these results. I want to just say a couple of quick words about this. Look at this first result that we have. This could be interpreted as saying is that mass creates gravitational flux. And if you look at the formula for flux, it's mass. Under some constants. It's negative, indicating the gravitational field is pointing inward. This is a constant, right? 4 pi is a constant. G is a constant. So other than constants, mass is what creates gravitational flux. Interesting. This is morally just kind of a local version of the same formula. Mass creates flux. Mass density creates flux density. Remember we talked about divergence as being flux density. So this is arguably just a density version of this other formula. That's pretty cool. Okay. There's one little shortcoming I do want to clean up. This formula that we were just talking about there that we just derived, that's, that was the hard one, you might say. That formula as computed there only applies to spheres, right? We took major advantage of the fact that this was a sphere in order to do this calculation. Right? For one thing, that magnitude of x is a constant. For another thing, that the normal vector is computed by that formula. That relies on this being a sphere. So you might say, okay, well, yeah, but how often is it that we're actually interested just in spheres? Well, okay, fair enough. So here's a following calculation. And that is to observe that you take that divergence formula that we just derived, and if you take a triple integral of both sides of that equation, we knew that divergence was this constant times mass density. Take just a triple integral of both sides, right? Taking a triple integral of both sides, check it out, you have here a triple integral of divergence. Well, that's flux. And on the other side, you have a triple integral of density. That turns into mass. And so, punchline, this same formula, even though as I derived it, it only applied to spheres, because I was able to turn that into a local fact about not just flux, but flux density, I can apply it to, therefore, any solid and its boundary surface. So really, really powerful facts. Here's a couple of examples. You could argue that this is kind of a silly example, but nevertheless, it's kind of interesting. So suppose we have a surface that's an outward-oriented sphere centered at the center of the sun and with a radius of 100 million miles. Quick reminder, the radius of the Earth's orbit is on the order of 93 million miles, so the Earth's orbit is just kind of barely inside of this great big huge sphere centered at the sun. So what's the total gravitational flux through this surface? Well, then you think to yourself, well, my gosh, the sun is creating a gravitational field. I can compute that flux. But so is Mercury. So is Venus. So is, I want to say Venus has a moon, I think. I forget. I'm not sure. Let's say it does. I'll have to look that up later. Oh, wait, did I write that down here? No, I guess not. So, but there's Earth, and Earth has a moon. Right. And that's pretty much all the mass inside of that surface. So all you have to do is add up those masses. The sum of those masses is m, and flux is computed by this simple formula there. So it turns out to be a really easy question. You want to compute flux of a gravitational field? Just count the mass inside of your surface and multiply by negative 4 pi g. Okay. All right, now here's a more fun example. This is one of my favorite examples in the whole book. This is what I like to call the Death Star example. I used to call it that when I was first teaching multivariable calculus, because when I was growing up, Star Wars was a big deal. And then there was this, 20-year gap or so where Star Wars kind of wasn't a thing anymore, and it was just like this narrow niche of my generation of people that were into Star Wars. And of course now it's back, right? Big time. So anyway, let's imagine this is the Death Star, or whatever. Let's see, in episode 7, didn't they have kind of a Death Star-like thing? I forgot what they called it. I'm not as up on this stuff as I should be. Oh, what was it?
Circular base.
Is that right? Okay. So I've forgotten. So the idea, anyway, here's what I really need for mathematical purposes. All right, I need to have a spherical shaped thing that where all the mass is on the outside, it's hollow in the middle. Right? And I feel like the original Death Star episode 4 Death Star was hollow in the middle, but anyway, it would have been a lot easier to build having it hollow in the middle. lot less mass. So anyway, we're gonna go with this. So we have a shell of mass, and I want to know what is the magnitude of the gravitational field inside that shell of mass. Now, let's try to back of the envelope this. Right? And you think to yourself, okay, well, look, this point here where we are at, for example, is really close to this part of the surface, and so, oh man, there's going to be a lot of gravitational pull there, really strong gravitational field coming from these bits of mass over here. But here's the thing. All of this mass over here, it's further away by quite a bit. But look how much more of it there is. So here we have more mass pulling from a greater distance. Here we have less mass pulling from a shorter distance. Who wins? By how much? Right, it's not obvious. It's hard to figure. Right, you can try to imagine, imagine you're floating around inside of here. Just like, what would it feel like to float around inside of a hollow shell of mass? And I have to tell you, I don't have that much personal experience in that, right? So intuitively, I have no idea. Right? I can't relate to the question even. We're going to be able to answer this question. So let me show you how this comes together. So first thing I'm going to argue is that the gravitational field, it definitely doesn't point off axis, right? That's just a symmetry argument. I mean, it can't point off axis. For one thing, if this mass were to start spinning, gravitational field is not going to, I mean, as it moves, effectively, it's still mass arranged exactly in the same way. So the gravitational field has to be something that doesn't change when you spin the sphere. So that means the gravitational field has to be spherically symmetric or rotationally symmetric. So it's got to be on axis, like that. Right? And also, likewise, it's got to have the same magnitude when you're the same distance away. Now, who knows what might happen further out? Maybe there's a different magnitude over here. I don't know. Right? But on any given inner sphere of given radius, the magnitude of the gravitational field's got to be the same. Just symmetry. Okay, so the way we write that down is this. Now, note all of this says is if the gravitational field is in the direction of the position vector, so it's radial, and the magnitude only depends on distance from the origin. So so rho being, of course, distance to the origin. So I don't know what this little function f is. Little f, no idea. Nevertheless, I feel like the gravitational field's got to be of that form. Okay. Okay. So let's write down. Now keep in mind my goal. My goal was to figure out what is the gravitational field itself. We will get to that. Right? But the easy way to compute the gravitational field is to actually first compute something different. We're not going to compute the gravitational field itself first. We're going to start by computing the flux through that sphere. So we have this, this inner sphere here. Let's see, color. I'll use yellow. No, I'll use red. So let's look at that sphere. I'm going to compute the flux of the gravitational field through that sphere. Okay, well, here it is. Flux. And that's our formula for flux. But we just got through agreeing that our gravitational field has to be of that form. So we're not just computing a flux of some random gravitational field, we're computing a flux of a gravitational field that has this spherical symmetry to it. Right? It's got to be radial, and the magnitude can only depend on distance from the origin, distance from the center. ds vector, of course, is n times ds scalar. Okay, so there's our formula for flux, and a couple of quick observations. This being only a function of radius, and we're on a sphere of that radius, that'll factor right out of the integral, so it's a constant as far as the surface integral is concerned. And then let's see, x dot n, will these two vectors point in the same direction? They're both radial, so you just get the product of the magnitudes, which of course is rho. And this rho here is a constant. It pops out. Over that sphere anyway, rho doesn't change because that's how spheres work. Right? And then what remains then is surface area, which is, again, 4 pi rho squared, old news. So, punchline, here's a formula for that flux. Now, wait a second, though. How could this be the formula for the flux? The flux through this sphere, we just got through concluding up here that flux is computed by that formula. Flux is negative 4 pi gm, where m is the amount of mass inside of our surface. Well, how much mass is there inside of this surface? How much mass is in there? Let me remind you, the mass is all over here. Right? By assumption, this Death Star or whatever thing it is, this is a spherical shell. All the mass is around the outside. There's no mass in here. In this yellow solid, no mass. Per the example that I just referred to, no mass, no flux. Right? This flux through this red sphere has got to be 0. So the flux is equal to two things. On the one hand, the flux is equal to that. On the other hand, the flux is equal to 0. That means that this thing here is equal to 0. How could that be? How could this expression be 0? Well, if that expression is 0, either 4 is 0. Okay, that's silly. Don't be silly. Pi might be 0. No, of course not. Rho might be 0. No. We're looking at a non-trivial sphere here. The only thing it could possibly be 0 is this thing, namely that thing, and that tells me that our vector field is 0. So that's the really shocking result. I think that's it's borderline hilarious. That if you have mass arranged in a spherical shell, now it's got to be a sphere. I emphasize the arguments that we made here. We made big use of the idea of symmetry. So it's got to be a spherically arranged mass, right? Spherically symmetric, constant thickness, density, whatever you want to say, right? So the symmetry is critical, but in that case, on the inside here, gravitational field is 0. So there's some homework exercises where you're going to do analogous calculations to what we just talked about. Various different versions. Here's one version that you can consider. What would be the gravitational field here? Right? Suppose you're standing there on the outer surface. How much gravitational field would there be? Well, that's a non-trivial question, and you can make an argument, which is, well, think about the sphere going all the way around the outside, and you could argue, a symmetry argument around that purple sphere. Write down a formula for the flux, and then ask, well, how much mass is there inside of that purple sphere? That's, whatever it is, the total mass of the Death Star, right? Whatever that is. It's probably online somewhere, right? One of these Star Wars forums. Somebody's got some estimate of the mass of the Death Star. And I've set these two things equal to each other, and there's your gravitational field. I'll give you a hint. The result of that calculation is that the amount of gravitational field there is there on the outer surface is exactly the same as it would have been if all of the mass had been concentrated at the center. That's how it turns out. Which gets tossed around in high school physics classes, and maybe this is a personal experience, but I was told when I was in high school physics class that was obvious, and I didn't get why that was obvious. You can just move these masses around, and it doesn't change. It seems aggressive. Not clear to me why that's true, and it wasn't clear, right? My teacher didn't know this argument that we just made, and was reading it out of the book, and the book said it's true, therefore it's obvious. Well, I think that was the rationale that was going on. But anyway, it's really, really not obvious that it's true, but it is true, and it's also, it's just, again, like kind of stunningly, how could that be? It just seems so, a little too convenient or something that would work out. Okay, all right, so these are really cool arguments. Note the very heavy use that these arguments make of Gauss's divergence theorem. There for one thing, here for another thing, right? In both of these warm-up problems that we did, that we used, right? The fact that we could ignore mass outside of the region uses Gauss's divergence theorem. The fact that only the total mass and not the arrangement of mass affects flux is a consequence of Gauss's divergence theorem. So none of these arguments are possible without Gauss's divergence theorem. Okay. All right. So I hope you all will enjoy those exercises. They're pretty cool. Quick observation about electric fields. I don't know if y'all, again, you may or may not have had a physics course previously, but there is this thing called an electric field. There's an electric attraction between charged particles. If you're not aware of this, don't worry about it. It's just a fact about physics that if you have a positive charge and a negative charge, a certain distance away from each other, there's an attractive force. It's kind of like gravity in a way. One of the big differences is that if you have two positive charges, then it's a repelling force, not an attracting force. So it's not exactly like gravity, but so it's got a plus and minus kind of factor on it. Anyway, it's an attractive force. It's a force between two particles, let me say that. And now let me just talk about the formula here. Notice that it is inverse square and radial, right? Directly between the two objects. So here's the amazing thing. Mathematically, except for the fact that there are negative charges, mathematically, this formula looks just like the formula for the gravitational force. So you can write down an electric field, just like a gravitational field, that's going to be inverse square. It's going to have the same mathematical structure as the gravitational field. It's going to have that same cube in the denominator. And all of the arguments that we just got through making about gravitational fields, you can make all those exact same arguments about electric fields. It's pretty cool. So you get all these same results. I'm just going to go through them. I think it'd be a really nice exercise to try to go through and get these conclusions on your own. Just going through by analogy with what we just argued about gravitational fields. But anyway, here's the results. If you look at the electric field created by a point charge, the divergence is 0. That's morally equivalent calculation. It's really the same calculation with different constant that gets multiplied by 0. So it's, same calculation. Flux of an electric field, if the charge is outside of the surface, is 0. Doesn't matter how charge on the inside of a surface is distributed. Just redistribute that charge however you like. It won't affect the flux. The divergence of the electric field is proportional to the charge density. Just like with the gravitational field. Different constants, of course. Okay, so here's some of those specific punchlines. There's the formula for the electric field. Note, it's got this same inverse square dependence on distance and radial. Divergence is proportional to charge density. There it is. This thing, rho, is classically used to represent charge density, so I'll use it the same. It's a little unfortunate, right? Because rho we think of as a spherical coordinate, so it's too bad. But anyway, this is commonly used to represent charge density. Oh well. And likewise, you can take a triple integral of both sides of this equation, and you get that the total electric flux, the total flux of an electric field through a surface, is proportional to charge. It's just like gravitational formulas. The only difference being that there's different constants, right? So that constant's different, that constant's different, these constants over here, a little different. Other than that, same show. Okay. So let's talk about Maxwell's equations for just a minute. This is one of Maxwell's equations, right there. This is called the differential version of that, one of Maxwell's equations. There's a different version of this equation. Let me say that a little bit differently. There's another Maxwell equation that is closely related to this equation. It's so closely related to this equation that we call it a different version of the same equation. That's how close these formulas are to each other. And that other equation is this one. Now, at a glance, they don't look to be particularly closely related. All right? This is about a derivative. This is about an integral. What are you talking about? Right? But let me remind you, this says flux is proportional to charge. This says flux density is proportional to charge density. When you say it like that, now you can see how closely related these are. So, in fact, you can get from one to the other here. You can get from that one to that one by taking a triple integral of both sides. triple integral of both sides of that equation. Forgive my abusive notation here, but if you take a triple integral of divergence, you get flux. You take a triple integral of density, you get quantity. And so, now of course on the left side, the triple integral of divergence being flux, that's Gauss's divergence theorem. So the thing that makes the close connection between these two different equations is Gauss's divergence theorem. If you don't understand Gauss's divergence theorem, you can't connect these to each other. But with Gauss's divergence theorem, you see that they're almost instantaneously connected. Just take an integral of both sides. I mean, it's almost like they're the same equation. Just this is local and this is global or something like that. So again, this is how they're referred to. These are referred to as two different versions of the same equation. This is called the integral version, and this is called the differential version. They're thought of as being morally kind of the same equation. There's a similar deal with magnetic fields. Here's a formula for the divergence of a magnetic field, which is mysteriously zero. Magnetic fields are weird. This is not a physics class, so I'm not going to go into all of that funny business, and I'm not going to try to motivate where this comes from or anything. But anyway, this is a fact about magnetic fields. And here is another true fact about magnetic fields, which again, at a casual glance, you'd say, well, totally different formula. This is divergence. This is flux. They're totally different constructions. Okay, yeah, true, agreed. But that's flux. This is flux density. Now you see they're actually very similar looking equations. And again, the connection between them, the way you get from the one to the other, you take a triple integral of both sides of that equation. Triple integral of divergence, my Gauss's divergence theorem, gives you flux. Okay, so they're not thought of as being two separate equations. They're thought of as being two different versions of morally kind of the same equation. Okay. There's a two-dimensional version of Gauss's divergence theorem. I'm going to leave this as something for y'all to read. It's, time's a factor in this class. We only have so much time. And as much as we have left to cover, I think the best use of class time is to not spend it on this. It's a pretty straight read. So I'm going to leave y'all to read this section on the two-dimensional version of Gauss's divergence theorem. So give that a look. Punchline, it's pretty much exactly the same as the three-dimensional version, slightly different formula. Okay, and we're going to move on now to Stokes' curl theorem. I'm going to go kind of quickly through the derivation, or I should say the motivation, right? The pitch for where does Stokes' curl theorem come from? Because it's the same thing that we've done a bunch of times here already. Let me remind you. Here's our R3 diagram. Right, we have these three different columns. We've talked about what happens when you look at columns 0 and 1. If you take the boundary of a curve, can you relate that evaluation to a line integral over the original curve? And that motivates this being the gradient operator right here in fundamental thermodynamics. Then we made a, pretty much analogous argument over here. Started it last time. If you take a solid three-dimensional region and look at its boundary surface and take a flux, can I do that as a triple integral? And if so, a triple integral of what? And we motivated that there was a divergence operator there. Gauss's divergence theorem comes up. Well, now we're going to play the same game here. I mean, it's just morally equivalent. You could probably work this out on your own just from the pattern of except for the final step of the details. We're going to think about a surface. We're going to look at the boundary of that surface. Now let's think about that for a minute. If you have a surface, the boundary of the surface is a curve. In fact, a closed curve. Right? So we're going to take a surface, look at its boundary curve, think about a line integral of that boundary curve. That's now a closed curve. So line integral around a closed curve, remember we called that circulation. So given a surface, we're going to look at the boundary circulation. And we're going to ask, can I write that as a flux of something? And if so, a flux of what? What do I do to that vector field to get the thing whose flux equals the circulation? Same exact pattern. Okay. No surprise, we're going to take a surface, chop it up into little pieces, because, well, that's what we've done in every other previous case. Right? Or there's not a lot of creative new ideas happening here. We're applying one idea in a bunch of different contexts. We have this worry about accumulation. Is it true? Now, and again, not obvious. Certainly not obvious. But if I take the boundary, the oriented boundary of one piece of surface, right? That's an oriented piece of surface. If I take the oriented boundary of one piece of surface, and if I take the oriented boundary of another piece of surface, that's right next to it. If I take the green oriented boundary and the blue oriented boundary, when I add those up, do I get the same thing as the oriented boundary of the whole thing? In other words, if I were to look at the entire surface, look at its entire oriented boundary, would I get the same thing? So let me draw those pictures again. Okay, let's see if I can do this. Is green plus blue equal to purple? Well, you can see there's a lot of potential for this to be the case. I mean, that piece, that blue plus this green gives me that purple, and this green is that purple. Green plus blue is purple. It looks like it's lining up. Everything seems to have the potential to be true, to work out. Our only sort of issue is that there are these two extra pieces here, where I have that edge appearing twice. And, well, yeah, true, right there. There are extra terms when I'm looking at the boundary of S1 and the boundary of S2. Yeah, there's a couple extra terms here. And they cancel because they're oriented in opposite directions. And again, this is not a coincidence. This is unavoidably a consequence of how we defined boundary orientations. Right? The fact that I defined orientations to be counterclockwise, or thumb, right-hand rule, however you want to say it. The fact that you defined these orientations to be like that, that's what makes this, even though they're both counterclockwise, that means that from the perspective of one side, but it means that from the perspective of the other side. And so we get that familiar cancellation. So punchline, yes, boundaries of oriented surfaces accumulate, just like in every other context that we previously saw. Okay, so that gives us, again, we've been through morally this kind of a calculation a bazillion times. Here's boundary accumulation. If you have a large surface, and you cut that large surface up into a bunch of little smaller surfaces, and the boundary of the whole surface is the sum of the boundaries of all the little pieces of surface. That's what we just concluded. Boundaries accumulate. All the interior edges cancel, just like in Greeks. And, geometrically different, but morally the same as in Gauss's theorem and fundamental theorem of line integrals, blah, blah, blah. So, boundaries accumulate, therefore fluxes accumulate. Why did I say flux? Circulation. Sorry, I was still in Gauss mode. Circulation accumulates as well. So the circulation around the boundary of the whole surface is the sum of the circulations around the boundaries of the little pieces that you chop it up into. Okay. This is always a constant. It's always the same no matter how you slice it. If you take a limit of it, you're taking a limit of a constant. Limit of a constant is the same constant. Said differently, you can take the limit for free. Again, that's exactly what we did in the previous context. This is starting to look like a surface integral at this point. Of course, it's not exactly. We need to have a surface area over there, so we multiply and divide by the same thing. Now we have here a surface integral. I'm a little concerned about the fact that it's not a vector surface integral. I was kind of hoping this would turn out to be a flux. And as of the moment, I've got it written as a scalar surface integral, and that's a little upsetting. It's not what we were hoping for. But let's see what happens. We find ourselves, again, trying to figure out what is the integrand here. What is the limit as we slice finer and finer? What's the limit of this expression? Let's take a moment to remind ourselves what this is. This is circulation. Right, we've got a little piece of surface, some tiny little piece of surface here. We're looking at the circulation around the boundary of the little piece of surface. So some little piece of surface, we're going around the edge like that. I'm going to compute the line integral circulation around that little piece of surface per unit area. And then the limit as this gets smaller and smaller. Well, as your little piece of area gets smaller and smaller, we've taken a circulation around a really short curve. It's getting the circulation is getting smaller and smaller, but the area that you're dividing by is also getting smaller and smaller. So there's this question of, in the limit, as you're slicing smaller and smaller, what happens to that as a proportion? And this is where I'm going to sweep it under the rug. There's details. You can work it out if you'd really like to. I don't think that's really where the focus should be in this course, myself. So I'm just going to assert what this is. This thing, this integrand, is computed by this formula. And it's very plug and chug. Note how this formula here, it's all partial derivatives. Isn't that handy? All partial derivatives. Specifically, partial derivatives of P, Q, and R. Partial derivatives of the components of the vector field. Weird fact to notice about this formula, though, it's not just dependent on the vector field. That's something that you compute from the vector field, but there's this other kind of factor here, and that is the unit normal vector. So that's a little bit strange. This integrand here, the limit of circulation per unit area, seems to depend on how the little piece of surface is oriented. So your little piece of surface, right? Keep in mind if you have a little piece of surface, there's a normal vector just pointing perpendicular to it. At the same place, if I were to look at this little piece of surface and just kind of turn it, I didn't really move the piece of surface. The surface is still in the same place it had been, but because it's pointing a different direction, I'm going to have a different normal vector that'll make this dot product dramatically different. Okay. And if you think about it, it's not the craziest thing in the world. We're interested in circulation. Circulation says to what extent is the fluid flowing around our thing. So circulation, imagine our vector field. If I want to know to what extent the vector field is circulating this way, you wouldn't expect that to be the same as the amount that the vector field is circulating in a different way. You would expect it to be different. So anyway, that's what the formula ends up being there. And we plug this into there. And our expression here turns into that. And we have a theorem. Circulation, this accumulating quantity of circulation is a flux Here's the resolution of that previous worry. We were worried about the fact that that this was just a scalar ds, but now I ended up multiplying it by n. Now we do have a ds vector, and you see we actually have then a flux of this thing. This thing here. So this is called Stokes' curl theorem. The thing that we're taking the flux of is called curl. So this, our integrand here, is called the curl of the vector field. We're going to talk a little bit in a few minutes about what, how to visualize that, what that looks like geometrically. Anyway, there's the formula for it, curl. Okay, cool. A little bit of notation. Y'all remember this business. We rewrote divergence by making a sort of eyebrow-raising choice to give a name to this, to this thing, like as a vector, as if that's okay, which, by the way, is a really super common choice, perfectly justifiable. It's fine, right? It's a little uncomfortable at the beginning, but this vector of partial derivative operators we call del. Interpret gradient as being what happens when you apply this del operator directly to a function. You can interpret divergence as being what happens when you dot this with a vector field. Okay, well, it turns out that you can think of curl in a way that relates to this as well. And I don't know if you can necessarily see this coming, but let's see, we have a vector field here with components that have two terms of something, some operator times, some operator on one function minus some operator on another function. It looks like a little 2x2 determinant in each entry. We have then a vector whose entries are all 2x2 determinants. Doesn't that sound like cross product? And it turns out that it lines up just exactly right. If you take the del operator and your vector field, and if you cross them, remember the formula for a cross product is it's a symbolic determinant, right? E1, E2, E3, blah, blah, blah. You get exactly curl. Just turns out that way. So this is an alternative notation for curl, very, very common. People use this all the time. Curl is alternatively written as del cross f. I really like this notation. For one thing, it's just a little bit fewer pencil strokes than writing out the word curl. It's shorter. Okay. And there's other good mathematical reasons for wanting to do this that we're not going to talk about in this course. But it's really very natural, important way. So heads up, you're going to see this notation. Again, in my second major second major in physics as an undergrad, I saw this notation quite a bit more than I saw that notation. Okay, so very, very common. This is what you're going to see most of the time. And that's the notation I'm going to use here in the book. So here we go, putting it all together. Here's our theorem, and here's our appended diagram. So the theorem there, circulation, boundary circulation, is computed as a flux of this thing called the curl vector. And on the diagram, here's where we were. We were thinking about this part of the diagram. If I take a surface, if I look at the boundary curve, and if I think about the line integral, so in fact the circulation around that boundary curve, that boundary circulation, can I think of that as a flux? And if so, flux of what? Answer yes, it's a flux of this thing called curl. And so we have now our new operator, the curl operator, and here's our theorem, Stokes' curl theorem. And just a reminder of the pattern. If you take a surface, take its boundary, take a vector field, compute the curl, then the circulation of the vector field through the boundary, the flux of the curl through the original surface, same thing. pattern just keeps continuing. Okay, so I hope everyone has noticed the pattern, is comfortable with how the pattern goes. All of these different theorems, they look so much alike, right? And this is what I feel like is underemphasized in a lot of multivariable calculus books. Is they'll write down all these theorems, but they won't talk about how, oh my gosh, they're doing the exact same pattern. It's the same argument. It's morally identical argument just applied in a different context. So I try to focus on that a lot. So anyway. Okay, so some examples. Suppose I want to compute a line integral. Got a vector field given. Got a curve that's parameterized. Now let's talk about our options here. We actually have a bunch of options about how we might go about computing this line integral. For one thing, first option on the table, I suppose, is always brute force. You could always attempt, anyway, to chapter 5, a line integral. I'm going to take this vector field, I'm going to parameterize my curve. Hey, here the curve's already parameterized. We're partway there already. It's almost like the statement of the question is suggesting that you should go with using the parameterization and chapter 5 brute force, crank it out. And then you notice that, well, your integral would get a little bit ugly, though, because x and y are sine and cosine, or cosine and sine here. So, your vector field, it's not clear this is going to be a doable integral. Might be an inconvenient integral. Looks like it will probably be an inconvenient integral. Okay, so that's a possibility. Now, here's another option. We've got a line integral. Maybe in order to compute this line integral, how about maybe the fundamental theorem of line integrals? Right? That seems like a reasonable candidate. We had big success back in section, let's see, what is it, 6.2, I think it is, right? Section 6.2. We computed several line integrals very powerfully with the fundamental theorem of line integrals. Here's another line integral. Maybe we do that. Now, it turns out that doesn't work as it ends up. And I'm going to leave some details for you all to discover on your own. But what would happen if you tried to use the fundamental theorem of line integrals to turn this line integral into, well, just some function? Notice, of course, the big if on using the fundamental theorem of line integrals is, does my vector field have an anti-gradient? Is there a function whose gradient is my vector field? If you want to turn this into that, you need to go backwards through the gradient arrow. You need to find an anti-gradient. Not all functions have anti-gradients. Excuse me, not all vector fields have anti-gradients. And as it turns out, this vector field does not have an anti-gradient. And I'll be able to tell you soon, in fact, possibly tomorrow, either tomorrow or Thursday, one or the other, how I know that this vector field does not have an anti-gradient. But it doesn't. If you try to play the game on this one, you're going to lose. It's a losing game. Don't even try. Or go ahead and try, but be prepared for loss. It's a losing game. Okay, so brute force, unappealing. Fundamental theorem of line integrals doesn't apply. So we got to think about our other option, and our other option is Stokes' curl theorem. So I'm interested in computing this, one of those. Here's a theorem that says, hey, I can turn that into a flux. All you got to do is take your vector field, compute the curl of it. Right? There is, of course, an asterisk. There's asterisks on all these theorems. The asterisk here is our curve. Is it a boundary? Is it a boundary of some surface? Or the way I like to say it sometimes, can I take my curve and can I find an anti-boundary? Like, is there a surface whose boundary is that curve? The theorem says right here that Stokes' curl theorem only computes line integrals for boundary curves. Only boundary curves. It's got to be a boundary. Again, not a minor technical point. we need it to be a boundary of some surface because that surface is the surface through which we compute flux. It's not that the theorem doesn't give you a true answer if you don't have an anti-boundary surface. It's that the thing crashes and burns and doesn't even make any sense if there is no anti-boundary. Right? So if we're going to use Stokes' curl theorem, the very first thing we have to do is look at this curve, parameterized like so, and decide, is that a boundary of some surface? And if so, what surface? So here's our picture. Y'all recognize this parameterization, of course, right? Cosine and sine, z-coordinate 0. Not hard to persuade yourself that this curve, here, let me do this in green, I suppose. This curve like that. So we just have to look at the picture, use our geometric intuition. Is this curve the boundary of some surface? And good news, yeah, it is. It's a boundary of, for example, it's a boundary of that surface. Now we got to think about orientations, right? I mean, whatever surface we pick, that surface, we're going to have to compute the flux through that surface. Flux means I need an oriented surface. So does this thing go up or down? Well, you have to think about the right-hand rule, and you think about our conventions for how orientations go. If I were to say that this is oriented downward, well, if it were oriented downward, thumb, fingers, swirl, that would induce an orientation on the boundary curve that's going the wrong way. Right? So this yellow surface oriented downward, the boundary is not the same as the green curve. The boundary is the backwards of the green curve. So downward is the wrong orientation. If I were to say that this yellow surface is oriented upward, what's the boundary of this oriented surface, yellow surface orientation? Well, thumb, fingers, swirl. It does give me the correct orientation on that curve. Right? So you got to think it through. Use your right hand only. Don't try to get efficient and do it with right and left at the same time. Doesn't work, right? Right hands only. Right? So think about the two different possibilities and make sure you pick the correct orientation on the surface that you're describing. So anyway, here it is. The surface is this surface. So the line integral we've been asked to compute, that line integral is not just a random line integral, that's a line integral around a boundary of a surface. Or said differently, this is a circulation around a boundary of a surface. And that's what allows me to invoke Stokes' curl theorem. There's Stokes' curl theorem. I've now turned my line integral into a flux. Good news, flux is easy to compute. You take your vector field, plug it into there. Curl turns into that, 0, 0, 2, and you have yourself an easy flux integral to compute. Right, so this, no big deal. Saves you a bunch of trouble. Okay, we're out of time. We'll pick up here on tomorrow. Wednesday. Yeah. See y'all later. Sorry to go over time. I lost track of time.